Coming to the properties of a wave function, we have the probability density, which is given by this psi star psi. So this is the probability density, which is given by psi star psi. And what does this mean? The probability per unit length or unit area or unit volume. Now what does this mean? Area, length, area and volume. If the wave function is defined in one dimension, then we say that psi star psi is probability per unit length. If it is in two dimension, we say that it is psi star psi is defined in or probability per unit area, or if it is three dimension, we call it is probability per unit volume. Now this example is a 1D box, and here we have a 2D box or two-dimensional linear harmonic oscillator, and in the case of 3D we have a hydrogen atom. Okay, so and so now what does probability is defined for? Now probability between x to x plus dx is defined, or it is written in the form of psi star psi dx. Psi star is the complex conjugate of psi, complex conjugate of the wave function psi. If psi is real, if the psi is wave function is real, we have psi star is equal to psi. Now the total probability is given by integral x1 to x2 psi star psi dx. Now this will give you some value of the probability p, which will be always which should be always less than 1 if wave function psi is normalized. If the wave function psi is not normalized, we would get the probability equal to or greater than 1, or if not normalized. Properties of wave function. Psi must be finite. Now this is what does it say? As x tends to plus or minus infinity, the wave function psi should be moving to 0. That means it must be convergent, that is psi is converging as x tends to infinity. Now this is the first property. Second one is the wave function psi must be continuous and single valued. The wave function psi is continuous and single valued. That means at any point in this wave function, we cannot have it should be a smooth curve, and it cannot be something like this going and coming back. So if something it is like this, means at this particular point x equal to a, you have two values or two probabilities. At this particular point you have two values of wave function psi, which is not possible. So psi must be continuous and it also should be single valued. Okay, now this is the third point. Now that is dou psi by dou x, the first derivative, partial derivative of psi with respect to x should be continuous and again single valued. That means the first derivative is nothing but the slope of the wave function has to be continuous and single valued. Now the fourth point is the psi must be square integrable. Okay, Now from plus infinity to minus infinity, when you integrate psi star psi dx, this particular value should give you a finite number when you integrate from minus infinity to plus infinity, or wherever the psi is defined. Psi is defined. If you take the integral psi star psi dx, this particular value should be finite one. And this is the fifth point. 1 by psi dou psi by dou x, 1 by psi dou psi by dou x, this is called logarithmic differentiation. And this logarithmic differentiation also should be continuous. Normalization for any wave function psi is done to convert to the to make the probability equal to 1. Unless the probability equal to 1, the wave function doesn't carry much information. Now sum over s, ps should be equal to 1. That means the total probability should be equal to 1. That is integral from minus infinity to plus infinity psi star psi dx should be equal to 1. This is for in general. If the limits are from x1 to x2, that means the wave function is defined in the interval x1 and x2. Integral from x1 to x2 psi star psi dx should be giving value equal to 1. Now for 1D box, the normalization constant or the wave function is given as psi is equal to a sine n pi x by L, where n represent the order or state in which the particle is present. N equal to 1 means ground state, n equal to 2 represent the first excited state. So and the L, it is nothing but the length of the box. Then the normalization constant A, which is given here, is equal to under root 2 by L, where L is the length of the box. Now for an exponential function, the wave function psi is equal to a e to the power minus a mod x. Okay, now this value of a is equal to root of coefficient of mod x. So in this case, the wave function psi is equal to root of coefficient of mod x is nothing but a into e to the power minus a mod x. So this is the normalization constant for exponential function, and for 1D box it is root of 2 by length of the box. L is nothing but the length of the box. Suppose we are finding out the here we have a 1D box whose this is 0, this is minus L, this is plus L, then the normalization constant A for this particular 1D box will be equal to root of 2 divided by length of the box. What is the length of the box from here to here? That is equal to 2L. So it is root of 2 divided by 2L. Okay, so remember this L represent the length of the box. For a Gaussian function, we have the general wave function formula as psi is equal to a e to the power minus ax square. So Gaussian function will be something like this. We have the x-axis here and y-axis over this. So something like this is our Gaussian function, and this is the center of the Gaussian function x equal to 0. This is plus infinity, and here you have the minus infinity. And the normalization constant A is given by 2 by pi into coefficient of x square to the power 1 by 4. Now according to this wave function, we can write the normalization constant A equal to 2 by pi. Coefficient of x square is nothing but A, and so to the power 1 by 4. And here we have the hydrogen atom. For the general wave function is A e to the power minus r by a naught. R is the variable radius, and a naught is the Bohr radius. The normalization constant A is equal to 1 divided by under root pi a naught cube, and dV, this is in 3 dimension spherical polar coordinate system. dV is given by r square dr sine theta d theta d phi. Probability. So this is another session from quantum mechanics. Probability is given by the formula as we have discussed earlier. It is P is equal to integral from x1 to x2. This is where the point where we have to find the probability, psi star psi dx. Now here we have the 1D box which is in ground state, which means n equal to 1. Then for a 1D box, now this is one more parameter we have to define here. It is unsymmetric box. It is unsymmetric means it is from 0 to L. The length of the box is from 0 to L. So from 0 to L, if you consider the probabilities in each of the following session, that means from 0 to L by 4, the probability is 1 by 4 minus 1 by 2 pi. From probability from L by 4 to L by 2, it is from 1 by 4 to 1 by 4 plus 1 by 2 pi. From L by 2 to 3L by 4, it is 1 by 4 plus 1 by 2 pi. And from 3L by 4 to L is 1 by 4 minus 1 by 4 minus 1 by 2 pi. Now if you consider the probability from 0 to L by 2, you have to add these two probability from 0 to L by 4 plus probability from L by 4 to L by 2. So if you add both, what you are going to get is 1 by 2 pi will go, so you can get 1 by 4 plus 1 by 4, that is 1 divided by 2. Now you can also get questions like probability from 0 to L by 4 and probability from sum of the probability from 0 to L by 4 and 0 to 3 by 4 L to L. That means in this range, in this region as well as in this region, that means the first and the fourth region, what is the probability? So first and fourth region, the probability is 1 by 4 minus 1 by 2 pi plus 1 by 4 minus 1 by 2 pi. So that will be equal to 1 by 2 minus 1 by pi. So this is how you can get to the probability. If at all there is some other parameters, that means whatever is not given here, you can use the limits. If something is asked, 3L by 8 to 7L by 8, this is a possible question. Psi star psi dx, so you have to integrate and substitute the limits, which will give you the probability from 3L by 8 to 3L by 8 to 7L by 8. So this is how you can get probabilities. For the same 1D box, if you are treating with a wave which is of in the first excited state, that is n equal to 2, the probabilities from 0 to L by 4, L by 4 to L by 2, L by 2 to 3L by 4 and L are 1 by 4, 1 by 4, 1 by 4 and 1 by 4. Now the total probability you can check, this will be constituting 4 times the 1 by 4, so that's equal to 1. And small note here, you have, if the particle is in a 1D box of length L is in nth state, that means the particle is in nth state, and if we are asked to find out the probability from 0 to, if this is L divided by n, then the probability is equal to 1 by n. One example we can take, if the particle is in fourth state and we are asked to find out the probability from 0 to L by 4, then the probability will be always equal to 1 by 4. That means 1 by n, n equal to 4. Most probable value of the wave function. Now probability is nothing but psi star psi. If you want to find out the maximum value or the most probable value of psi star psi, you have to differentiate this psi star psi with respect to x and equate it to 0. Now after doing that, you may get some equations, and you may have to find out the values of x. For example, x equal to a, x equal to b, you may get depending on the power of x. Power of x, if it is x 1, that means only linear, you may get one value. If it is x square, you may get two values, that is quadratic, you may get two values. Or if it is x cube, if psi star psi is x cube, you may get three values of x. Okay, so now once you get these values, you have to substitute x equal to a or some value in this wave function psi. So you get the wave function, the most probable value of the wave function. Now for example, here we have the hydrogen atom which has a wave function depending on r radius, that means only radial dependence. Psi of r is equal to 1 divided by pi a naught cube e to the power minus r divided by a naught. The a naught is nothing but the Bohr radius. Okay, then the most probable value of r in hydrogen atom is nothing but r equal to a naught. That means this is the point where you can find the uh, electron maximum. Now therefore the most probable wave function of the hydrogen atom is at r is equal to a naught. Now so put the value of r here as a naught, you will get at psi at r equal to a naught equal to is equal to 1 divided by pi a naught cube e to the power minus 1, or 1 by e. So this is the most probable wave function for hydrogen atom, which is 1 divided by pi a naught cube into e to the power minus 1. Expectation values. Expectation values or average values. Now the expectation value of an operator O is the eigenvalue of the wave function for the corresponding operator, which is nothing but the O. Now here if you consider A as the operator and psi as the wave function, A psi equal to lambda psi, which gives you the lambda as the eigenvalue or the average value. Okay. Now A is the operator here, lambda is the eigenvalue or expectation value, or it is also called the average value. Now here are few eigenvalue or variable corresponding operators are also given. For position we have x as the variable and x cap as the operator. Momentum p, which is nothing but I minus I h cross dou by dou x. The kinetic energy p square by 2m, which is equal to, as operator we can write it as minus h cross square by dou x square. Here you need to divide by 2m also. This is kinetic energy. Now energy, it is I h cross dou by dou t. Expectation value of A is given by this bracket, triangular bracket we put across the operator A, which is equal to integral psi star A psi d tau or dx dA or d tau. It can be anything if psi is normalized. Now this is only when the wave function psi is normalized. If it is not normalized, we have to use the expectation value of A equal to lambda, which is equal to integral psi star A psi d tau divided by integral psi star psi d tau. This will give you the expectation value. For 1D box of length 0 to L, so for 1D box we know inside the potential is equal to 0 and the wave function psi is not equal to 0. The wave function is given as psi is equal to A sine n pi x by L, and we know that the normalization constant A equal to under root 2 divided by length of the box, which is nothing but the L. The expectation value of the x or the average value of x is nothing but L by 2, so which is nothing but somewhere over here, and x square, expectation of x square is L square by 3 minus L square by 2 n square pi square. This is the expectation value of x squared. For the similar box, 1D box, from minus L by 2 to L by 2, which again the length is equal to L, total length from minus L by 2 to L by 2, the total length is L. Now the wave function psi is a cos n pi x by L. So since it is symmetric box, since it is L by minus L by 2 to plus L by 2, it is called symmetric box. The wave function is given as psi equal to a cos n pi x by L. For odd values of n, this can be used for odd values of n, and we have to use a psi is equal to a sine n pi x by L for even values of n. Now here the expectation of x, so it is also somewhere, it is in the middle, which is equal to 0. So expectation x equal to 0, while expectation of x square is equal to L square by 12 minus L square by 2 n square pi square. For 1D box, the expectation value of P, the momentum, is equal to 0. The expectation value of P square is equal to n square pi square h cross square by L square. Now we can also write one more point here. We know that energy is equal to kinetic energy for the 1D box, which is equal to P square divided by 2m. So this you can write it as expectation of P square divided by 2m. Now just substitute this P square from here. We will get 1 by 2m into, so P square is n square pi square h cross square by L square, so which gives you n square pi square h cross square by 2mL square. So this is the total energy of the 1D box for the state n. For the linear harmonic oscillator, we have the wave function psi is equal to a e to the power minus ax square. The normalization constant a equal to 2 by pi into coefficient of x square, which is a here, into whole to the power 1 by 4. Now the expectation value of x equal to 0. The expectation value of p is also equal to 0. Expectation of x square is 1 by 4 times a, and expectation of p square is h cross square a. This is the center of the linear harmonic oscillator. If the wave function is given as psi is equal to a e to the power minus of a into x minus x naught whole square, then this x naught is called the center. Then expectation of x will be equal to x naught if it is for the if the center is not 0, then expectation is you can write expectation x is nothing but the center of Gaussian function. Yeah, here we have these in detail. If the center of the Gaussian function is at x equal to x naught, then you can write the wave function as psi is equal to a e to the power minus a x minus x naught whole square. So here x naught is called the center. Then expectation of x equal to x naught, expectation of p will remain 0. Expectation of x square will have 1 by 4a plus x naught squared. P square, expectation of p square will be h cross square a. For hydrogen atom, we have the wave function psi is equal to 1 divided by pi a naught cube e to the power minus r by a naught. The expectation value of r, r expectation is equal to 3 by 2 times a naught. Expectation of 1 by r is equal to 1 by a naught. Expectation of r square is 3 a naught square, and expectation of 1 by r square is 2 by a naught square. Now just for the extra note, we can write the expectation of r is equal to integral psi star r psi d tau. Why d tau? Because we are dealing with hydrogen atom, which is a three-dimensional problem. So we have integral psi star r psi d tau is nothing but r square dr sine theta d theta d phi. So which means you have to integrate psi star psi r cube dr into integral sine theta d theta and d phi. So this becomes the triple integral, and this is how you have to solve the expectation value problem from 3 dimension.